Today we will establish the relationship between the number of spheres close packed and the number of voids generated. Let us consider the hexagonal packing. Here red ball represents the A layer and yellow ball represents the B layer. After forming the second layer, two different types of voids will be created. One is known as tetrahedral void and another is known as octahedral void. Now let us consider this central red ball. This red ball is surrounded by four tetrahedral voids. It is common between four tetrahedral voids in this figure 1, 2, 3 and 4. This tetrahedral void is created by three red ball in first layer and one yellow ball placed on the top of the first layer. This tetrahedral void is formed by the three red ball in first layer and one yellow ball which is placed on the top of this depression, forming a tetrahedral void. Now again this tetrahedral void is formed by the three red balls in first layer and one yellow ball placed at the top of this depression. So this sphere is surrounded by three tetrahedral void and one tetrahedral void will be formed above this plane when these three yellow balls are placed over it. So above this plane, this sphere will be common between four tetrahedral void, and similarly this sphere will be common between four tetrahedral void below this plane. So the total number of voids surrounding this sphere, total number of tetrahedral voids surrounding this sphere will be equal to 8, 4 above the plane and 4 below the plane. Now let us consider the octahedral void surrounding this sphere. There are three octahedral voids surrounding this sphere. This octahedral void is formed by three red balls in first layer and three yellow balls in the second layer. Similarly, now let us consider this octahedral void. This octahedral void is surrounded by three red ball in first layer and three yellow ball in the second layer. Similarly, this octahedral void is formed by three red ball in first layer and three yellow ball in the second layer. Similarly, this octahedral void is also surrounded by three red ball in first layer and three yellow ball in the second layer. So this red sphere is common between three octahedral voids in above this plane and three octahedral void below this plane. So this red sphere is surrounded by, it is common for within 6 octahedral void. It is surrounded by 6 octahedral void, 3 above this plane and 3 below this plane. Now let us see with the help of the model. Now consider this hexagon. If we place this 6 ball in close contact with the central ball, a hexagon will be formed. During this type of packing, 6 depressions will be created above this plane and 6 below this plane. 1, 2, 3, 4, 5 and 6. Suppose let us place a sphere. These 3 balls, when they are closely packed together, a depression will be created, and if we place a 4th ball on its top, a tetrahedral void will be formed. Similarly, out of these 6 depressions, if we place 3 yellow balls at the alternate depressions, a B layer will be formed. A layer is represented by red ball and B layer is represented by yellow balls. So we can cover only 3 depressions, and these depressions will create a tetrahedral void where 3 red balls are placed in the one plane and the yellow ball is placed over the depressions, and the void created between these 4 balls is known as tetrahedral void. So this red ball is common between 3 tetrahedral voids. Similarly, we can place 3 yellow balls below this plane, and then this red sphere will be common between 3 tetrahedral void formed below this plane. Let us see from this model again. Here it is AB type of packing. 3 red balls below the plane and 3 yellow balls placed below the first layer and 3 yellow balls placed above the first layer. So 3 tetrahedral voids will be created by placing 3 balls above the plane, and 3 tetrahedral voids will be formed below the plane by placing 3 spheres below this plane. Now let us place one red sphere above this triangle and one. Let us see this figure, this model. Here this red sphere is the central sphere present in the hexagon. Suppose this one. This red sphere is the central atom. It is surrounded by 3 yellow balls above the plane and 3 yellow balls below the plane. This red sphere is common between, it is creating 2 tetrahedral voids, one above and one below. So the total number of tetrahedral voids surrounding this red sphere is 4. 1, 2, 3, 4 above the plane and 1, 2, 3, 4 below this hexagonal plane, and hence this sphere is surrounded by total 8 tetrahedral voids. Now, and 6 octahedral voids, 3 above the plane and 3 below the plane. Let us consider from the figure again. If we place these 3 balls, 3 octahedral void will be generated here. When we cover 3 voids by placing 3 yellow balls over the hexagonal plane, these 3 voids which are not occupied, or the depression which are not occupied, will create the octahedral void in the second layer. When we place these 3 balls above the octahedral voids, it will form the ABC type of packing. Let us see. This represents the ABC type of packing. So the void created here will be the octahedral void. So this red ball is common or surrounded by 3 octahedral void above this plane and 3 octahedral void below this plane. This red ball is surrounded by, or sphere is surrounded by 3 octahedral void above this plane and 3 octahedral void below this plane. And we know that a tetrahedral void is surrounded by 4 spheres. This tetrahedral void is surrounded by 4 spheres and the octahedral void is surrounded by 6 spheres. This is octahedral void, it is surrounded by 6 spheres, and this is tetrahedral void which is surrounded by 4 spheres. Now let us see, there are 2 particles having 2 different sizes. This is larger in size and this one is smaller in size. If we place this larger particle above these 3 depression and try to place the sphere above it, 4th sphere above it, it cannot be stabilized. It means the size of the particle is large, so it cannot be accommodated in the tetrahedral void. But if we place a smaller particle, we can easily place the 4th sphere above it. It means the tetrahedral void is smaller in size. Now let us see the octahedral void. Here the size of particle is much larger as compared to this one also and this one also. This is very small as compared to this one. So if we place this particle in octahedral void, it can be easily accommodated and we can balance these 3 spheres above it. It means the tetrahedral void is smaller in size as compared to the octahedral void, and this tetrahedral void is formed by the 4 spheres surrounding it, and octahedral void is formed by 6 spheres surrounding it. Now let us establish the relationship between the number of spheres packed and the number of voids formed. So the number of tetrahedral voids per sphere, we have seen that it comes out to be 8. Let us see again. This sphere is surrounded by 4 tetrahedral void above this plane and 4 tetrahedral void below this plane. So this sphere is surrounded by total 8 tetrahedral voids. The number of tetrahedral void per sphere will be equal to number of tetrahedral void around this sphere. How many tetrahedral voids are surrounding this sphere? There are 4 tetrahedral voids surrounding this sphere above the plane and 4 below the plane. So this sphere will be surrounded by total 8 tetrahedral voids, and the number of sphere around the void, and we know that the tetrahedral void is surrounded by 4 spheres. So the number of spheres surrounding the void is equal to 4. Now find out the ratio between the number of tetrahedral voids around the sphere divided by the number of spheres around the void. The total number of voids surrounding this particular sphere is 8 tetrahedral void. Surrounding this sphere is 8, and a tetrahedral void is surrounded by 4 spheres. So the number of spheres surrounding the tetrahedral void is 4. 8 divided by 4 will give you 2. Now let us see from this formula. The number of tetrahedral voids per sphere is calculated as the number of tetrahedral voids around a sphere divided by number of spheres surrounding the void. Here this sphere is common between 8 tetrahedral voids. So this sphere is surrounded by 8 tetrahedral voids, as we have seen from the model as well as with the figure. So the number of tetrahedral void around the sphere will be equal to 8, and a tetrahedral void is surrounded by how many spheres? 4 spheres. So divide this 8 with the help of number of spheres around the void, and that is 4. 8 divided by 4 will give you 2. So the number of tetrahedral voids per sphere will be equal to 2. Now let us calculate the number of octahedral void per sphere. We have seen that each sphere is common between 6 octahedral void, 3 above this plane and 3 below this plane. 1, 2, 3 above the plane and 3 below the plane. So a sphere is surrounded by total 6 octahedral void. Now let us calculate the formula. The number of octahedral void per sphere will be calculated as the number of octahedral void around the sphere. How many voids are surrounding a particular sphere in this packing? 6 octahedral void. A sphere will be surrounded by 6 octahedral void, And an octahedral void is surrounded by how many spheres? An octahedral void is surrounded by 6 spheres. So 6 divided by 6 will give you 1. In this way, hence we have find out that the number of if the number of closed packed sphere is n, the number of octahedral voids generated will be equal to n, and the number of tetrahedral voids generated will be twice of n.